Well, thanks for inviting me to give this talk today. I'm going to be talking about the provision of lighting for captive amphibians, and there's going to be a particular emphasis on the provision of UVB radiation. Some talks on lighting can get quite technical, but my aim is not to go into a lot of technical detail, but to cover the basics and to focus on more of the practical applications. So to begin with, I just wanted to dedicate this talk to two people in particular. Frances Baines on the left. She's a world-class veterinarian that's really taught us a lot about the provision of light for amphibians in captivity, particularly UVB radiation. And then Matthias Gotz at Jersey Zoo, who has dedicated a lot of time as well into this particular field. So to begin with, I want to talk about the different types of light. So we have infrared heat. We also have visible light to humans, which is 400 to 700 nanometers. We have, UVA, which is 320 to 400 nanometers, which is visible to many animals. And we have UVB, 280 to 320 nanometers, which may also be visible to some species. And then finally, we have the biologically significant wavelengths of UVB. These are the ones that we're worried about, which peaks at 297 nanometers. And finally, we have UVC radiation, which is a dangerous type of radiation, which isn't actually, doesn't tend to reach the Earth's atmosphere. It doesn't tend to reach the Earth's surface because it's blocked out by our atmosphere. So just to kind of show that on a figure here, you can see the very small amount of UVB radiation on the far left that is within the biologically significant range that we're going to talk about later. So when we talk about providing lighting for amphibians, we have to work on several assumptions. One is that amphibians have evolved to make the best use of their environment, and we should be adopting husbandry practices that are informed by field collected data. And also that light, including UV, is a free and plentiful resource, and that animals have to self-regulate their exposure to heat, light, and UV like many other environmental parameters. And so the optimal levels of light, including UV, are likely to be those that are experienced in nature by an animal when the conditions are favorable. However, data on specific microclimates are currently lacking, and that's an area that we need to gather more data on to inform husbandry practices going forward. And when we talk about amphibians, they're obviously found in a huge different variety of habitats, from quite arid, open areas that will receive high levels of UV, to quite dappled forest environments, and then high elevation sites, which are often quite high in UVB radiation. And then when we talk about different types of amphibians, many amphibians are aquatic, and UVB does actually penetrate through water. It depends on the amount of turbidity in the water, but it can penetrate the water column quite deeply. We've got amphibians with complex life cycles, so their needs for lighting may change over the course of their lives, from life as a larvae through to a post-metamorph. And then we've got amphibians that will live in the canopy as well. So there's obviously a diverse array of species and living in diverse habitats, but it's not enough to just know the habitat or the part of the world where a species is from to inform how we provide lighting, how much, and photo period and so on. We need to think about the specific microclimate for an amphibian. So looking at this little cross section of the rainforest here, we can see that even in a given habitat, that there is huge variation. And our husbandry practices should, in an ideal world, be kind of catering towards the microhabitat of a particular species. And when we think about about amphibians, we can't, and lighting, it's not a case of one size fits all. We need to adopt this species-specific and evidence-based approach wherever possible. So I'm going to start off by talking about how amphibians see the world. So the structure of the amphibian eye is very similar to many other vertebrates. And they are often very visually orientated animals with color vision. And we see that, they forage based on movement, for example. It's highly likely, there's some studies showing that amphibians can see into the UVA spectrum. We'll talk about that more later. And that there are mechanisms for non-visual light detection in amphibians. So they have a pineal complex. They also have a Harderian gland in the eye, and also there may be photoreceptors in the skin, which can detect light. So, for example, there's been studies on Ichthyophis Sicilians where they've illuminated the tail of the Sicilian for a few seconds, and that's resulted in the Sicilian moving away under kind of laboratory conditions. So, and that there's a growing evidence that some large species of salamanders, for example, they also have these photoreceptive cells in their or structures in their tails, which is obviously of importance when we think about refugia for animals in captivity. And it's also suggested that the lateral line systems of some amphibians may be light sensitive, and potentially the neuromasts too. Some amphibians are also able to fluoresce, which was quite an interesting recent finding. So the way amphibians see the world is totally different to the way that we see the world. So we must always think about how amphibians see the world when we are thinking about how to maintain them in captivity. And the more the research that's published, I think it's evident that there's a whole lot that we don't know about amphibians, how they see the world, and how to actually care for them in captivity. So light is important because, as I said, many amphibians are visually orientated. It can help kind of regulate circadian rhythms. It could potentially be a breeding trigger, different light levels. And it's of physiological importance, and some wavelengths, and we'll talk about that later. So when we think about amphibians, for example, here we've got phylomedusa frogs. These guys are adapted to withstanding quite strong light, and they have waxy secretions which will protect them when they are quite exposed. And then some amphibians will bask in the full sun. And given that amphibians have permeable skin, basking amphibians often sit in water. So as water is lost, they're able to absorb it. Other amphibians will spend time underground, but even these will benefit from reflected UVB radiation, and we'll talk a bit more about that later. So even when an animal's in a cavity, it will still be receiving many of the wavelengths that are present. And finally, many aquatic species, like this Oriolalax tadpole, they may have dark pigmentation because they're living in habitats which are fully exposed to the sun at high elevation. So they have this dark pigmentation to protect them from UV radiation. So there's quite a diverse array of ways in which amphibians are coping with their environment in the context of light and heat, because they're often interrelated. Many amphibians are obviously nocturnal, and under low light conditions, we do know that amphibians do have good color vision. So recent research has found that color patterns in some neotropical tree frogs function for species recognition, so they are of great importance. And many people, when they, at least historically, when they've been maintaining nocturnal frogs, have been using either red or blue lights to kind of recreate moonlight. And often people say, working in the field, if you use a red light, that that it's less disruptive for the animals. They behave normally, but the blue wavelengths of the light signal to the brain that it's day rather than night, and this can disrupt the circadian rhythms. So it's important that in captivity we don't provide blue or red light for amphibians at night, but we provide very faint, warm white lights, potentially from an LED. So, as many amphibians are nocturnal, their activity patterns and their behaviour may be influenced by the brightness of the moon. And there's some studies to show that behaviour is different for species depending on the lunar cycle. So on or the brightness of the moon and cloud cover. So male European tree frogs called less, and females laid less eggs during bright nights. And then we can kind of look at roadkills to infer activity in some amphibians. So in the rib newts, there were more roadkills in darker nights, and the inverse was true in fire salamanders. So again, there's not one size that fits all. We have to be thinking of species-specific approaches when we think about how light affects the different each species. So evidently more research is needed as always. Then when we think about breeding amphibians, we can have amphibians that are fossorial species that live underground and very unlikely to be exposed to light. And I think this example is probably quite pertinent when it comes to talking about UV radiation. So we've got a species of microhylid frog here that spends large amounts of time underground. So you may think it may not need much light or much UV radiation, but when these amphibians are breeding, they may spend a couple of days out in the full sun, and this may actually be enough for, this may be kind of significant for them for the lights to meet the light, the radiation that they receive, the different wavelengths of radiation that they receive to meet their physiological needs going forward for an undetermined period of time. So when we're now going to focus more on the UV radiation component, the UVB radiation, and I think this is a really good read. It's published in the open access journal JSAR, and yes, it was originally kind of the study was done focusing on reptiles initially, but there is some, it's relevant to amphibians too, and there's some case studies with amphibians at the end. So this was a tool that's been developed to try and inform and guide and document UV radiation, the levels of UVB radiation specifically that have been provided for amphibians in captivity. So I strongly recommend that you read this paper if you haven't done so before. So when we talk about UV, many people it's synonymous with amphibian declines, and it's one of the factors that have been cited as contributing to amphibian declines. And sorry, just having a bit of a technical issue. But as we've seen earlier, that many amphibians have adaptations to deal with UV exposure, such as pigmented eggs, pigmented skin, or waxy secretions. And most studies which have actually looked at whether UV is actually a contributing factor to amphibian declines have been measuring UV radiation at waist height and not in the specific microclimate of amphibians. So many of these studies are actually flawed because they're not recording where the levels of UV radiation that the amphibians would actually be exposed to. And so in captivity, I think it's always, yes, it can have deleterious effects. And so if you're going to provide UVB radiation, we need to be conservative about the amount that's provided. It needs to be offered in a gradient, and fundamentally, it needs to be monitored. So when we talk about this biologically significant wavelengths of UVB, these have direct effects on the skin, and they're a really effective disinfectant. They can destroy bacteria and fungi and viruses, some of them anyway. It can help modulate the cutaneous immune system. It increases pigment formation. And you know that kind of good feeling you get when you've been out in the sun. It has that, sunlight has that feel-good factor because of beta endorphin synthesis. And it also strengthens the skin barrier functions. So looking at how this works, and I'm really sorry, there's something that's gone on with my PowerPoint, and I don't know how to pause these animations. So sorry to keep skipping backwards and forwards. It's probably annoying you as much as it is me. But when sunlight hits the skin, and again, it's these biologically significant wavelengths, it kind of kickstarts a process. So it causes the kind of the photolysis of provitamin D3, which is then thermally isomerized to vitamin D3, which then goes into circulation. There's actually another way that D3 can enter the body, and that's through the dietary mechanism. So amphibians can get vitamin D3 through their food. And then the vitamin D3 is stored, is hydroxylated to calcidol, where it's stored in the liver. And then this calcidol is then synthesized, calcitrol is synthesized from calcidol in the kidneys. And this is really important for calcium metabolism and many functions of the bones, intestines, immune cells, reproductive tracts. And actually, every organ system that's been studied to date has vitamin D3 receptors present. I think that's really important because we probably underestimate the benefits of vitamin D3. And I mean, you know, just looking at some of the news reports as well at the moment when we're talking about kind of COVID-19, there's some very kind of preliminary studies on the effects of vitamin D3 and human health and susceptibility. And yeah, also vitamin D3 is metabolized into calcitrol throughout the body. And what we know that calcitrol is really, really important in gene transcription, and these genes can influence multiple functions throughout the body, from growth the immune system as well. So it's really, really quite important. However, when we think about the amphibians in our care, we need to think about, again, not to adopt a one-size-fits-all approach, that different species will get their source of vitamin D3. Some, for example, troglodytic species like the olm are never going to be sunbathing, they're never going to be basking. So it's highly likely that if they have a D3 requirement, they'll be getting it through a dietary mechanism. Whereas kind of species of frog that bask and are exposed to the sun's rays, they're more likely to be getting more vitamin D3 from the sun rather than dietary means. But there are some studies that may kind of contradict what I've just said. So there's a recent study on dart frogs, which showed that frogs always chose to call, male frogs chose to call from perches that receive low UVB radiation, and that frogs maintained their positions longer on the perches that received the lowest levels of UVB radiation. And then, as I mentioned earlier, that there's some research and evidence that amphibians can see into the UVA spectrum. The researchers that were doing this work then kind of increased the levels of UVA and this resulted in the frogs moving away, because they think that the frogs can kind of see high levels of UVA, and they'll avoid it to avoid the damage that they may be caused from overexposure to UVB. However, what this study doesn't show, it doesn't kind of, I guess, demonstrate, is the fact that even low levels of UVB can be beneficial. So it's not saying that it's bad, it's just saying that frogs avoid high levels of this particular wavelength of light, or at least that's what it is suggesting. So regardless, UV radiation probably plays an important role in regulating some aspects of amphibian behavior. So getting the lighting wrong in captive amphibians, and in particular UVB radiation, we know that improper UVB provision can result in suboptimal calcium absorption, and that low circulating calcium levels can lead to nutritional secondary hypothyroidism. And this occurs when calcium is drawn out of circulation, drawn out of the bones, and because the need is greater in the blood. And this can really have a high impact on skeletal health, and bone integrity is then compromised. So you often see frogs with kind of deformities, frogs with bone fractures, or on radiograph, their kind of bone structure may not be particularly clear. They won't have very well defined bones at all. And eventually no calcium or very little calcium is left, and you may see kind of neurological signs in your amphibians, so kind of amphibians twitching, stretching out their limbs and spasming, which is pretty unpleasant to see. Obviously these clinical signs are clinical signs of other diseases too. So amphibians can actually, when we're talking about skeletal health, we think about when the situation has got so bad in terms of calcium deficiency that you're actually being able to see that the skeletal health is compromised. It's really gone quite far, and that calcium deficiency can, this is kind of the late stage when a diagnosis is made. Now, amphibians can store, and urine amphibians can store calcium in sacs in the cranial and spinal cavity. So you can see these kind of white dots along the vertebral column of this mountain chicken frog that's being post-mortem. And these are actually quite highly visible on radiographs. So you can see that we've got these calcium stores in the cranium and along the vertebrae. This one here has much better kind of stores than the animal that was being post-mortem. And you can also see that the bones here look relatively clear and well defined. But they're also able to store calcium in a layer below the skin, and that's both as larvae and as adults. And as larvae, during metamorphosis, these calcium stores are utilized. And also calcium is transferred from the female, the mother, to the yolk during egg formation. So I did mention that we know that many amphibians, or some amphibians at least, could probably meet all of their vitamin D3 requirements through dietary mechanisms. We know, but we do know that at least one amphibian can biosynthesize vitamin D3 through that chemical pathway that I explained earlier. That's one of the bombina, one of the fire-bellied toads. But it's an area that is really understudied. But we know that this process can take place in amphibians, this photobiosynthesis of vitamin D3, but we don't know how long the process takes. And that's quite an important thing to think about, and we'll talk about that a bit later. But we also know that dietary D3 provision may not meet the needs of some amphibian species in captivity. So we've worked with mountain chicken frogs for a number of years, and initially they weren't provided with appropriate levels of UV, but they were provided with food that was dusted with a dietary supplement that contained D3, and they still developed nutritional secondary hypothyroidism, which is commonly referred to as nutritional metabolic bone disease. However, this issue, so you can see that in the radiograph in the top left, the two radiographs side by sides, you can see there are historic and healed fractures in the legs of these frogs, and there's some kind of a number of different deformities. However, this issue was resolved, and you can see the radiograph of the frog at the bottom, which is skeletally healthy. And this was resolved with the provision of both UVB radiation of the kind of appropriate biologically significant wavelength, and the use of dietary supplements containing D3. So these are a couple of published studies that may be of interest. And compromised skeletal systems obviously have a direct impact on growth, prey acquisition, mobility, reproduction, and animal welfare. So the animals are able to recover. So if you rectify the situation and ensure that their nutritional needs are met, although we don't really know what the nutritional needs are of most amphibians, you can kind of provide additional emergency calcium, like a calcium sandose solution applied topically as well in extreme cases, but these deformities will likely remain even if the bones reossify. And when we start talking about translocation programs and using amphibians in conservation breeding programs for translocation purposes, I don't think we just need to be thinking about infectious disease to ensure that these animals are healthy and okay for release. We need to be thinking about skeletal health as well. So I believe that this kind of assessment is an integral part of pre-release health monitoring. And it's really confusing, isn't it, when you think about the huge diverse array of different lights that are available on the market, which ones to choose. They're often really, really, really expensive, and it's quite baffling. And often new brands are bought out. It's changing. It's really, really difficult to keep up with what's good and appropriate. And so one resource I'd recommend, although it's slightly off, parts of this website are offline at the moment, is the resource, the uvguide.co.uk. And this was developed by Francis Baines, who I dedicated this talk to at the beginning. And this site has a wealth of information. Again, it's primarily aimed at reptiles, but many of the same lighting products are used by amphibian keepers globally. So I strongly urge you to have a look at this website. And you can even kind of contact Frances. She's always very happy to help people that need advice. So some of the things that are on this website are actual tests of the different lamps that are available. So they actually measure the UV output at defined distances, so you can kind of get a good idea of the type of lamp that is appropriate for the enclosure or the species that you want to keep. And then I just wanted to talk about one of the kind of older methods that was used in amphibian husbandry, which was UV boosting. So this was kind of forcing the animals to be exposed to UVB radiation for a defined period of time to ensure that they all got their kind of monthly dose of UVB. And this probably was in part a cost constraint approach, because the lamps are expensive, and to have these kind of lamps that are pictured here on every enclosure could be a potential problem. But also just suddenly exposing amphibians to UVB radiation, and quite strong lamps, as in the case here, would be, this is a 300-watt lamp that was being used. It could be quite physiologically stressful for the animals, especially if they're, and also quite stressful if the animals don't really respond well to being handled and moved about. Can expose them to high temperatures, as I said. It also requires really close supervision. You don't want to walk away and leave frogs for kind of 15 or 20 minutes under this lamp. And then the time set by this method was quite an arbitrary length of time. I can't really remember what it was now, something like 15 minutes. And the trouble is, when I discussed that chemical pathway earlier on, we don't actually know how long it takes for the vitamin D3 precursors to be thermally isomerized in the skin. So you could be going to all this effort for nothing, basically. So this method is not really used now, but I just wanted to highlight it because I'm aware of a couple of collections in the UK that do still do this. So I would personally advise against it. So how do we decide how much UVB to provide? And again, borrowing information from the literature on reptiles, there's a really neat approach adopted by Gary Ferguson, which was published here. And he kind of, and his co-authors, they looked at different lizards in the US and they recorded the UVI in the UV index in the areas in which they basked, and then he kind of classified these lizards into different groups. So crepuscular shade dwellers, which had a lower UV range, right through to kind of thermophilic midday baskers, which were exposed to very high levels of UVI. So thinking about which one of these categories and the areas in between your amphibian fits in may be able to inform the way we decide what UVB to provide our animals with. And yes, I admit it's a bit of a stretch, but it's I guess a pragmatic way of making a choice when data from the field is often lacking. So we, again, this UV tool publication that I mentioned recommends two different methods for providing UVB: a shade method, which has a more kind of even distribution of UVB radiation, but always a gradient and at low levels, and then a sunbeam method for basking species, which may be some of the ranids and some of the tree frogs, where you've got a more intense beam of UVB radiation with a paired kind of high level of heat as well. Because the next point is that because the biosynthesis of vitamin D3 is temperature dependent, that thermal isomerization of the precursors needs warmth with it. So for actively basking species, you need to provide heat and UVB radiation in tandem. And yeah, so gradients are absolutely critical. So gradients of heat and UV, and these should be overlapping with the highest level of UVB corresponding with the highest temperature. And there's different types of lights available to meet your kind of needs. So it's a case of selecting the different lamps and combining them for the needs of your species. So for example, at London Zoo, we use the shade approach for lighting our dendrobatid frogs. We have quite a large area of low-level UVB with ample shade, and this kind of dappling effect with some small areas of kind of more intense heat is enough. And we have to trust that in the captive environment that we provided for these amphibians, that's relatively heterogeneous, that they're able to select the microhabitat that's most suitable for them. So we're giving the animals choice and gradients for them to self-regulate their exposure. So as I said, the UV gradient should be overlapping with the heat, the light, and the humidity gradient. So you have the strongest UV, the most intense light, the highest temperatures, and the kind of more dry area, I guess, overlapping together. Yeah, and that kind of reflects what the situation is in nature. And it's incredibly complex, because what we're actually trying to do is to recreate the sun, and the technology just isn't really there to do that. So in a simple, very simplified drawing, we need to ensure that these gradients are there, but we also need to ensure that there are refugia within these different areas, again, providing those animals with choice. So it's really important that when we talk about UVB radiation in particular, that there are places in the enclosure which have levels that would measure as 0, to ensure that the animals have the opportunity to get away from it, because, as I said earlier, it can be deleterious. And providing lighting for amphibians in enclosures can be quite challenging, especially for UVB, because many of the lids for enclosures will block UVB radiation. So things like plastic will block UVB, mesh will decrease the amount of UVB available. Also, in the top right-hand side, you can see that's a very small aperture available that will actually allow any of this light to penetrate into the bottom of the enclosure. And that just may not be sufficient for the needs of the animal that's living inside. So I quite like, personally, the kind of enclosure that's shown at the bottom with the very broad mesh top, because that gives you lots of different opportunities to provide different types and different combinations of both light and heat. So UVB declines with distance from the source, and it's lower at the edges of the source than in the middle. So if you look at, say, a fluorescent lamp and you were to measure the UVB output along the length of that lamp, it would be at its peak in the kind of middle 2/3 of the lamp, and then towards the end, it decreases. So we need to think about how we're positioning our lamps. It's also reduced by meshes and some plastics, as I said, and it's also stopped by glass. But there are some types of glass and plastic that are available that are UV penetrable. But the problem here is they often need to be cleaned as well. So we have, for example, in some of our reptile enclosures at London Zoo, we have a product called ETFE, which is a plastic that we use to as the roof of our Komodo dragon house. And it's meant to let UVB radiation through, and indeed it does, but we have to really keep on top of the cleaning to ensure that the animals are receiving the benefits of that. And also, you can increase the penetration of UVB radiation into the enclosure with reflectors, and I'll show you some examples of that in a minute. But one thing, if you are having UVB over plastic enclosures in particular, it's really important to know that UVB can degrade plastic over time and it can become incredibly brittle. So just bear that in mind, because the last thing you want is kind of a cracked tank lid with a hole in it and no amphibian inside. So again, providing UVB, we need to think of the enclosure size, because smaller species will require smaller grades of mesh as lids to keep the amphibian itself in the enclosure, but to also keep their food in the enclosure, things like Drosophila or springtails. And what that means is if you've got a small grade of mesh, that the lamp may need to be closer to provide the amount of UVB that you want and to achieve the desired gradients, and this can result in enclosures overheating, especially these small enclosures. So we need to think about the impacts that lighting have and not just focus on one particular component of lighting, such as the UVI index. We need to be thinking of temperature as well as lux. So I mentioned earlier about the reflectors providing additional kind of penetration of the UVB radiation. So you can see in the picture on the left that with a reflector at the same distance, the microwatts per centimeter square, so that's a measurement of all UVB radiation, is effectively doubled. And also the provision of a reflector can help focus the source of UVB, so it makes it less dispersed, as in the left-hand diagram that just came up, and more of a focus beam in your enclosure, which may assist you in providing gradients. And the really important thing we need to think about when providing UVB for all animals in captivity actually is what time of day are those animals active. So this graph here shows different amounts of the UVI index, which is the same index that may come up in your weather forecast to tell you whether or not you may need sun cream or not. This shows levels in the UK, in Wales, in December, very, very low levels below 1, but peaking at midday. And then the same location in the summer, much, much higher, peaking at just below 6. And then Alice Springs in November, so peaking at 13. But actually, when you look at the activity periods of many of the animals in these environments, they're actually only active, say, for example, at the beginning of the day or the end of the day. So they would never actually be out and about and exposed to those midday levels. They would be out and about exposed to the lower levels at the beginning of the day. So this is why it's really fundamental that we have a really good understanding of the natural history of the animals that we're working with, ideally based on field data, but also that we think about how to apply this when we're providing lighting for our animals in captive environments that are in our care. And another really nice study shows, which was done by my colleague Chris, who I think you've heard from on an earlier talk, and Richard as well, was looking at the mean UVI index in a site in Italy and the time of day. So it kind of shows that same thing, peaking in the middle of the day. And then what Chris did, a really, really simple study, is he looked at what time of day the frogs are basking. So he found that actually most of the frogs, the pelophylax that he was studying, they were basking towards the beginning of the day at a relatively lower UVI index. So this kind of data, relatively simple study, can help inform the way we would provide this form of radiation for the amphibians in captivity. So I think we should definitely be encouraged if we're living in areas where we have amphibians. It's very easy for you guys, myself included, to take this kind of data. However, I do want to urge a little bit of caution. So the next slide I'm going to show you was one of my errors with UVB radiation. So this is a Megophorus nasuta, an Asian leaf frog, and you can see it has quite a severe burn on the dorsum. And this is because when I set up a new enclosure for it several years ago, I measured the UVI index from the dorsal surface of the frog, so its back basically. And I didn't take into account the posture of the frog when they are moving about and active. And this frog has a very, very upright posture, and the kind of small projections above the eyes sit quite high. So even from like a 2 centimeter, 3 centimeter difference from the level that I measured the UVB radiation on the back to the kind of the point that the frog's head was, it was enough to cause quite severe burns. Luckily, this resolved, and I didn't feel too guilty about it for too long. But it's just, just to show an example of when it can go wrong. And I'm sure others have horror stories far worse. Also, I just wanted to actually mention something while I think about it. At the beginning, I said UVC radiation is something that we don't normally get exposed to it's obviously a very dangerous form of radiation because it's blocked by the Earth's atmosphere. But there are some lights that will emit UVC radiation. So those of you that are familiar with aquatic life support systems and UV filters, they use UVC radiation to kill off bacteria and algae in the water column. And I actually met someone once who used one of these lights thinking that they were for UVB radiation, and he killed a whole tank of tree frogs. So just a word of caution if we're working in a zoological setting where there's lots of different lights, just to make sure all the lamps are labeled very clearly. Another thing we need to think about is how sensitive amphibians, the skin of amphibians is. So making sure that if we are providing lamps and heat, that they're protected from it. So things like tree frogs, for example, they can bask up, they can kind of retreat as it's getting light before the lights in the enclosures come on. They can sit on lamps, and when the lamp turns on, they can burn. So it's really important that you have light guards such as this, but also bearing in mind that even though the light guard itself may protect the amphibian from the heat, if an amphibian was to sit on that guard and it was a UVB emitting lamp, it could be exposed to very high levels of radiation. So just thinking about how your animal is using the enclosure is really important. So monitoring is absolutely key. So there are two types of solometer for measuring UVB radiation. And so we have the 6.2. This is kind of the old school meter, but it's still used very widely because it very accurately measures the entire kind of UVB wavelengths, and it measures this in microwatts per centimeter square. And basically these units all have a sensor sitting on the top, and you angle that sensor towards the light source, ideally at the level of the amphibian, so you can get the appropriate reading. However, as I mentioned, in the kind of UVB radiation, there's a very limited amount that there's a limited kind of wavelength that's of biological significance that's going to basically end up with the result of the vitamin D3 being formed. And so this light, this meter, the solar meter 6.2 doesn't actually measure that. The solar meter 6.5 does. It's a kind of unitless measurement, it's an index, but this only measures the biologically relevant UV wavelengths. And so this means you can compare how good the different lamps are, because the readings using the 6.2 may vary drastically, but you don't know which part of the UVB wavelength that you're actually measuring, whereas a 6.5 is far more focused. So I would, if you're looking at purchasing a UV meter, this is the one I would recommend, because you can estimate the biological relevance. With that mistake I mentioned earlier, where I actually ended up burning a frog, there's a team in the UK now that have actually managed to remove the sensors from these UV meters and extend them on a cable. So this means we can get right into the microhabitats of the frog, and you don't have to fiddle around to get a measurement that's equivalent to the level of the frog by lifting the mesh lid. I'm sure those of you on the call that have experience with this kind of things realize how awkward it can be to get the measurement at the level at which the frog is sitting. So this kind of modification is quite useful. So if anyone wants any details of that, they can email me, and I can pass your contact details on to the person who's able to advise on the modification of the solar meters. Obviously the warranty would then not be valid, but I think they've done it quite a few times now, so they have good experience. So yeah, the monitoring is really, really important. Different lamps emit different amounts of UVB radiation, and some of the lamps on the market don't emit anything that's biologically significant despite the claims of the manufacturers. So you could be spending a lot of money for nothing. So it's really important, not only for the health of your amphibians, but for your budgets, that you're able to monitor the lamps and the amount of UVB that's provided. It can also be very variable with batch, and also lamps may emit massive amounts of UVB radiation when they're very new, and you may need to burn them in for 24 hours or so and actually measure them to get before they're kind of safe for an amphibian enclosure. And some good UVB lamps may be really difficult to obtain in some countries. So we have a project, for example, on Dominica, where we wanted to provide UVB radiation for our captive frogs, the mountain chickens. So we actually had to ship the lamps there because they just weren't available locally. I'm aware that time's running out, so I'm going to try and speed through this a little bit, but still have time for questions. But all of this, we've been talking about the adult life stage of an amphibian. But, you know, I think those of us working with amphibians in captivity, I think we really should and always be focusing on, you know, the larvae. If you have good tadpoles, you get healthy metamorphs, healthy adults. It all makes sense. But there's very, very, very little work done on the requirements of amphibian larvae in captivity, especially when it comes to light. And what's really cool is that regular kind of sandwich bags that you can buy over the encounter, they don't block UVB. So we actually managed to get field data through a colleague, Jaime Bosch, working in Mallorca. We've been working with Mallorca midwife toads for a while. They live in canyons that are exposed to in clear water. So the tadpoles are exposed to UVB radiation. They're darkly pigmented, which indicates that they've evolved a way to kind of deal with this. And so we actually took the reading from the UV meter without the plastic, then put the plastic on top of the meter, and we could then kind of calculate what the reading was when we submerged the meter inside the plastic bag. So we could then have inform a study that we did using kind of field collected data. And we exposed two groups of Mallorca midwife toads. We had two groups, a control with no UVB, and then another group with UVB. We provided them with the same lighting array, but over one enclosure we had a plastic which blocked all UVB wavelengths. And then when the tadpoles actually reached their kind of maximum size, they were euthanized and blood samples were taken to compare the kind of serum D3 levels between the two groups. And also then after they were euthanized, the bodies were then sent for mineral analysis to see if there's any difference between the calcium to phosphorus ratios in each of those species. So this study was ethically approved, and what we found, we didn't know what to expect, but we didn't find any differences in any of the parameters that we measured. So there was no differences, statistically significant differences between serum levels or the calcium content of the dead tadpole. There was no difference in growth of the tadpoles and no difference in the pigmentation. However, whilst we did use data from the field, we didn't collect data on temperature. So it could be UVB may be important, but we didn't provide the right thermal environment for the chemical pathway to happen or for long enough. So we actually only provided UVB for a few hours a day as well. So there is a need for further research, but this is the first study of its kind to look at the impact of UVB radiation on amphibian larvae. So just to summarize, I think it's really important that we are able to measure UVI, pair the UVI index, so UVB, with thermal gradients, approximate the wild in captivity, provide a gradient in captivity, be aware of interruption from materials, and regularly test lamps that we use at least every 6 months. And then just, again, we've talked a lot about neuron amphibians. We don't know anything really about UVB provision for any caudate amphibians or any Sicilian amphibians, although anecdotally we provided UVB for aquatic Sicilians and measured skeletal health over time, and there was no improvement, and the same for aquatic salamanders. But when we've done the same for anurans, about 26 species, I think, they all showed improved scales of skeletal health. So knowledge of lighting, as I mentioned, this is the last slide, is rapidly developing, so stay on top of the latest research, keep detailed records of husbandry changes and note failures as well as successes. Make sure that you budget accordingly for these lamps because they're expensive. Get outside and record data because we need to adopt more evidence-based practices as a community. And also there are limitations in kind of getting baselines on blood work. So actually knowing how much vitamin D3 is circulating in wild amphibians is really important.